Hello. Tá bom, faltando 5, né?
So our next speaker is Carol Aguiar from the Federal University in Minas Gerais. So I'll let you know.
Okay, thanks. So first of all, I would like to thank the organizers for the invitation to come here, for the opportunity to give this talk. I will talk about this work, correlation-driven Lifshitz transition at the emergence of the pseudo-gap phase in the two-dimensional Hubbard model. This work was done by my former student Helena Bragança while she was visiting Marcello Tivelli in France. We have also the collaboration of Shiro Sakai from Japan. And I myself, I'm at the Federal University of Minas Gerais in Belo Horizonte. No, I'm here, so we don't need a picture of me over there. Okay, so the talk is about the relationship between the Lifshitz transition and the pseudo-gap phase. I will give a brief introduction, especially since Marcello already talked before me and did this introduction, but I want to emphasize key points about the starting point of our work. So the context are copper oxide superconductors. We solve the Hubbard model using cluster dynamical mean field theory. And then I will focus on our work. I will present the phase diagram of the two-dimensional case. First, at have filling. The main result there is that we find two solutions, a metallic solution and a pseudo-gap metallic phase, which is metal stable. That is, it has larger energy than the metallic phase. So this means that, according to our results, we do have a mod transition in 2D because this phase is seen as the ground state phase at have filling. Then we go for doped systems, and there, when we have a strong interaction, the pseudo-gap phase becomes the smallest, the one with the smallest energy. That is, it becomes stable, but only up to a doping, which coincides indeed with the doping at which the Fermi surface changes from hole-like to electron-like. Okay, so this is the outline of the talk. First, the introduction. So the context is results on Cuprate superconductors. You've already seen this structure here. So we have that the copper and oxygen are arranged forming planes, like this one over here or this one over here. Okay, so we can consider the two-dimensional system. At have filling, we have 1 free electron per copper atom. So since we have stronger correlations, the state is a Mott insulator with AFM ordering, antiferromagnetic ordering. That's what we have here in this simple phase diagram of temperature as a function of doping. So if we have no doping, the ground state is a Mott insulator with antiferromagnetic ordering. As we dope the system, then we can have this superconductivity phase, but we also have this pseudo-gap phase, as Marcello already emphasized, and other people also emphasized here in this workshop. And in this talk, I will focus on this pseudo-gap phase. So not only the superconductivity phase is not well understood, but also this PD pseudo-gap phase is not well understood in the literature. Okay, so what is this phase? Just to define it once again, to repeat and emphasize what this phase is. So it's a phase where there is a suppression of spectral weight and opening of a gap only in some of the regions of the Brillouin zone. So here we have chi y as a function of chi x. We do not have suppression of the spectral weight here in this node region, but we do have it in these antinode regions. At 0 pi or pi 0. This is indeed the same here. So this is intensity for ARPS, angle resolved photo emission spectroscopy. So it's the intensity obtained as a function of energy. We see that how it evolves when we go along the Brillouin zone. So in this case here, we have a peak at the Fermi energy. This corresponds to this nodal region. If we go to the antinode, then we do see that we see this suppression of X spectral weight in these results over here. So this is the pseudo-gap phase. Only in some of the regions of the brilliant zone, we have this suppression of spectral weight. Okay, so to solve this problem, to describe this situation, we use the Hubbard model in 2 dimensions. So this first part gives rise to the kinetic energy. The electron can hop from site J to site I, so like it is represented here, or the other way around. We include, if the site is double occupied, then we have to pay an energy proportional to this U over here, so this accounts for correlation in the system. And here is the chemical potential. That's how we change the doping of the system. We consider both hopping between first neighbors, this is T, and also hopping between second neighbors, this is T prime. So I will show you results when we solve this Hamiltonian by using cluster dynamical mean field theory, and I will analyze 2 cases. One, at half filling as a function of T prime, and then we fix T prime equal to -0.1 and change the doping. In both cases, the phase diagram also has the dependency with the U, the correlation over here. So just to remind you, Marcello already gave more details than I will do for this cluster DMFT calculation. So the problem that we want to solve is set in a lattice, but since we have correlation in all the sites, this is difficult to solve. Then we map the lattice problem into a cluster of sites, only 4 sites. In these sites, we still have correlations, but the electron can hop to an effective path which is not correlated. And this simplifies a bit the problem. Okay, and then we also have this self-consistent calculation to perform with this cluster DMFT calculation. And in this work, to solve the cluster impurity, we use exact diagonalization. Okay, let us look at the results for the case at half filling. So why were we interested in this problem at half filling? We know that in 1 dimension, any value of U will turn the system to a Mott insulating phase, so that we do not have a metal insulator transition in 1D. So any value of U will give rise to a Mott insulator. In 3D, we know that according to dynamical mean field results, we have a critical value of U such that for values of U is smaller than the critical one, we have a metallic phase, and for values of U larger than the critical one, we have an insulating phase. So we have a metal insulator transition in 3D, right? This is in accordance with experimental results. In 2D, we know that the ground state is an antiferromagnetic insulator, but we may ask what happens if we do not have magnetic ordering. So if we are looking for the paramagnetic solution. This may be interesting for frustrated systems, right? So the question is there a Mott transition in the paramagnetic 2-dimensional Hubbard model? And if we look at the literature, the results are not clear. So we have both answers, yes and no. Okay, so here are examples of what we find in the literature. For some of the works, they do see a metallic phase and thus a Mott transition. So here we have a phase diagram of temperature as a function of U. There is a metallic phase for small values of U and an insulating phase for large values of U. So we have a metal insulator transition. In other works, we see that the gap persists to very small values of U. So they don't find metal insulator transition in 2D. So these are results of this first reference here. So it's the gap as a function of U. Even for very small values of U, they find a gap. These are our results. So for the Hubbard model at 2D, right, using cluster dynamical mean field theory. So this is U as a function of T prime. For small values of T prime, we have a metallic phase. It's this correlated Fermi liquid metal phase. For large values of U, we have the insulating phase as we would expect. But in this region here, we have a coexistence. This is the new result for us here, that in this region of the phase diagram, we have a coexistence between the correlated Fermi metal and a pseudo-gap metal. The pseudo-gap metal has larger energy than the correlated metal. That's why it is in parentheses over here. I will show you the difference between the energies soon. Okay? So if this has smallest energy, this is the ground state. So according to our results, we do have a metal insulator transition in 2D. Okay, let's look how can we know that indeed we have this coexistence and this is a correlated metal and this is a pseudo-gap metal. So here are results for the spectral weight, that is -1/π, the imaginary part of the Green's function. We are looking only in this antinodal point, that is, we are taking this k to be 0π. So here we have the results for the spectral weight as a function of energy in this point of the phase diagram. So this corresponds to T prime equal to -0.1 and U equal to 4. Okay, and that's the region. That's one of the points where we have the coexistence between the metallic phase and the pseudo-gap phase. So the black curve is for the pseudo-gap phase, and the red one is for the metallic phase. So we can see that at the Fermi level, the metallic phase has a finite value, and here we have a suppression of the spectral function. You may ask why this is not going to 0, and this is because of numerics. So indeed the calculation is done on the imaginary axis, and then we have to make an analytic continuation. That is, we take I omega to go to omega plus I eta, and we have to choose this eta to be small, right? So here are results for this pseudo-gap phase for 2 values of eta. So if we really put in a small value of eta, we see that the spectral weight goes to very small values close to the Fermi energy. But then we have a lot of peaks because we are using hexadiagonalization. So if we want a smooth curve, then we choose an eta a little bit larger, and that's what we have here. But still we have this suppression that is showing that indeed we have a pseudo-gap here for this black curve. This is for the spectral weight. Here I'm showing the imaginary part of the self-energy as a function of omega. So for the red curve, it's the same label. Red here is metallic, also red here is metallic. We see this Fermi liquid behavior, that is, the imaginary part of the self-energy goes with omega square. And for the black solution corresponding to the pseudo-gap, we see a different behavior. That is, we see this non-Fermi liquid behavior. Okay, so Marcello already told us that this pole in the self-energy would give rise to this suppression of spectral weight in this pseudo-gap phase. Okay, this is also happen for the insulating phase. We also have a pole, but it is more intense in the case of the insulating phase, as we can see here. So these are the same results I showed to you before for U equal to 4. Now I'm showing you results for U equal to 5. We are in this point of the phase diagram where we have a coexistence between the pseudo-gap phase and the insulating phase. So the pseudo-gap corresponds to the black curves and the insulating to the blue curves. And as I said, we have this pole also in the insulating phase, but which is much more intense, and we have the gap opening here in the insulating phase. Okay, here is the energy the total energy, kinetic energy plus potential energy as a function of U for t prime minus 0.1. So we are over this line of the phase diagram. The red curve, red symbols correspond to the metallic phase, and the black ones to the pseudo-gap. So we can see that both solutions have, are very close to each other in energy, but as I said before, the metallic solution has smallest energy, so this is the true ground state of the system. And the fact that the two solutions are very close in energy may justify the contradictory results that we have in the literature, that some of the groups say that we have a metal-insulated transition in 2D, and other groups say that we do not have. So according to our results, the metallic solution has the smallest energy, and then it's a true ground state, and then we do have a metal-insulated transition in 2D. Okay, this was for at half filling. Now let's dope the system. Okay, in the motivation to dope, of course, we have the phase diagram that the superconductivity appears when we dope the system. But we are not looking at the superconductivity in this work. We are looking at this pseudo-gap. But according to recent experiments, we have this result, that the doping P star at which the pseudo-gap ends coincides with the doping at which the Fermi surface changes from hole-like to electron-like. So let me define what this P star is, and then this change of the topology of the Fermi surface, and then I will show our results. So if you look at this phase diagram, which is temperature as a function of doping, we have this T star. So the pseudo-gap phase ends at this T star. And if we extrapolate this line to 0 temperature, then we find this P star. That is, the pseudo-gap is seen below this P star. What about the Fermi surface? How can I define the Fermi surface? So the Fermi surface separates at the momentum in space empty states from occupied states, right? If we look at the Green's function, we can write like here, and we can define the Fermi surface by imposing that this quantity, which we call the renormalized energy, at the Fermi energy is equal to 0. So when this quantity at omega equal to 0 is 0, we find the Fermi surface. So the question is, what is the topology of the Fermi surface? That is the sign of this quantity at when k is equal to 0 pi or pi 0. So in the non-interacting case, at heavy filling in 2D, we have that this is the Fermi surface. So we have that the renormalized energy at pi 0 is equal to 0. But when we dope the system or we introduce interaction, we can have both these situations. Either the renormalized energy at pi 0 is larger than 0, and then the Fermi surface looks like this, which we call an electron-like Fermi surface, or it looks like this if the renormalized energy is smaller than 0, the Fermi surface looks like this, and we say that this is a hole-like Fermi surface. And the doping, and this can, there can be a transition from one case to the other at a doping that we identify as LT, from Lifshitz transition, this is the Lifshitz transition, or FS, since it is related to the Fermi surface. Okay, so what the experiments tell us is that we can have P star, the doping below it, the pseudo-gap phase is seen, coinciding with the doping at which there's a change in the Fermi surface. We can see this, that this corresponds to the line where both quantities are equal. This is seen for different materials, even when we dope it or we apply pressure as represented by this arrow. Okay, so this is the experimental results. We have that the doping P star at which the pseudo-gap ends coincides with the doping at which the Fermi surface changes from hole-like to electron-like. Now we will show you our results. So this is the phase diagram I've showed already. So it's U as a function of T prime. Now we will fix T prime equal to minus 0.1 and change the doping. So this is the phase diagram that we get. U as a function of doping. For small values of U, we have again the coexistence between the correlated Fermi metal and the pseudo-gap metal. The pseudo-gap metal is still has still larger energy than the correlated Fermi metal. So this is what we have over here. But then if we increase U, then the pseudo-gap phase becomes stable. And also, if we increase doping, we see that here we had a Hole-like Fermi surface, and here we have an electron-like Fermi surface. And this happens together, the transition for the Fermi surface happens together with the transition from the pseudo-gap to the correlated Fermi metal. So indeed, we can identify here the two quantities that I defined before. P star is the doping at which the pseudo-gap phase ends, and PLT is the doping at which the Fermi surface, this is given by this red curve here, this is the doping at which the Fermi surface changes from Hole-like to electron-like. So here for small values of U, we have this, that this happens within the correlated Fermi metal, right? So in both cases here, we have the correlated Fermi metal, but the Fermi surface changes from Hole-like to electron-like. For larger values of U, we have what I said before, that both the PDM becomes the CFM, and also the Fermi surface changes from Hole-like to electron-like. Since this region for large U is the one that is important for cuprates, let's look at the results in more detail in this region. So here we have the spectral function at omega equal to 0. This is given by colors here. And we have ky and kx over here. And we can see that there is this suppression of a spectral weight at the 0 pi and pi 0, which is characteristic of this PDM phase. This is seen in ARPES results on this cuprate in the region where the doping is small. In this other region here, we have that this suppression does not exist anymore, so we have a spectral weight which is much larger in these antinodal regions, and that's why we have this correlated Fermi metal in this region when we increase the doping. Regarding the Fermi surface, we can calculate it by imposing that the renormalized and by looking at the values at which the renormalized energy is 0. So for small doping, we have a Hole-like Fermi surface, as I emphasized before, but I'm showing you the results to convince you about this. And here we have an electron-like Fermi surface. And this is in agreement with the experiments. So here, this is our phase diagram, right? And here are results that I showed you before of P star, which corresponds to this line in our calculation, and PFS, which corresponds to this red line, which we are calling PLT for the Lifshitz transition. So in this region, for larger values of U, we have a coincidence between P star and PLT, which is in agreement with the experiments. This is also in agreement with another paper that appeared in the literature, more or less at the same time as ours, by the group of Antoine Georges. So here they show the phase diagram. The plots are for the temperature as a function of the doping. For different values of T prime, the black symbols corresponds to T star. That is, on the left of this black curve, we have the pseudo-gap phase, right? And the blue symbols corresponds to the temperature related to the change in the Fermi surface. So that on the left, we have a Hole-like Fermi surface, and on the right, an electron-like Fermi surface. And what we can see, if we extrapolate to t equal to 0, we see that for t prime equal to 0, p star is close to PLT. This is also true for t prime equal to minus 0.1, and for t prime equals to minus 0.2, then p star is smaller than PLT. In our case, the calculation was done for t prime equal to minus 0.1, so we have an agreement with this result here. So p star coincides with PLT, as we can see here in the region of large U. So to conclude, we solved the two-dimensional Hubbard model by using cluster dynamical mean field theory. I showed you two phase diagrams, the first one at half filling. So it's U as a function of t prime. The most important result is that in this region here, we have a coexistence between the correlated Fermi metal and the pseudo-gap metal. The pseudo-gap metal has larger energy than the correlated Fermi metal, which means that we find a metal insulator transition into D according to our results. If we dope the system, then this is the phase diagram, U as a function of doping. In this region of large U, we have that the pseudo-gap becomes stable. And if we increase doping, then we have a transition from this pseudo-gap to this correlated Fermi metal. And also, at the same point, we have this transition from a Hole-like Fermi surface to an electron Fermi surface. If you want to know more, this is the reference for the published work. Thank you for your attention.
Questions? Oh.
Could you go to the previous slide, please? If I look on the top left, that's supposed to be t prime equal to 0.
Yes.
Why is the Lifshitz transition happening at a finite p, not at 0p? Am I not just going from a diamond to a hole-like and electron-like at half filling?
You thought that this should be over here? Is this your question?
Yeah. What?
Yes. So this arrow here is for the non-interacting case, and that's what you said, right? I don't know if you can see that there's a blue arrow over here, and this is the non-interacting case. Then it would be the case as you said.
Yeah. So in this case, you
this
have particle
is the
symmetries.
Hubbard model. It's the same model as we use it, but they use determinantal quantum Monte Carlo, and also another method. I think. But it's Hubbard model.
You see, in the Hubbard model, we know exactly the chemical potential that coincides with the half filling because of particle hole symmetry.
Yes.
Are you saying in order to get Lifshitz transition, you still need to dope away from half filling?
Yes. Well, indeed, these are not our results, but yes.
No, that's t prime equal to 0.
T prime is equal to 0 here. But is U equal to 7, so we are up here in this phase diagram. Doping, yes. This. It's this in this slide. So in the non-interacting case, it's like this. But if you add either interaction or doping, you change it.
Hi, Carol. Thanks for your great talk. Let me know one thing. You use a cluster instead of one single site, yes? And you are using a 4-site cluster, right?
Yes.
Okay, good. I believe that you can easily increase the size of your cluster up to like 8 or 10.
easily.
Because I know that you need to do self-consistent, so it's hard. But I guess 80 sites you can do at half feeling almost easily. I don't know. But the question is, can you increase your size? It's possible to increase your size in order to do something like a scaling analysis in order to extrapolate and see that if you really have this quantum phase transition for a mod and
yes, I don't know if you, Marcello showed some results where they were increasing the number of sites of this cluster. I think it's not very easy to do it, but it's possible to do. But and the results are, I think, qualitatively more or less the same. So there was a slide by him where he was citing works where they were increasing the number of sites there. Okay. No, we didn't check these results because the new result here is this coexistence between the correlated Fermi metal and the pseudo-gap metal. And then this coincidence between P star and PLT, right? But in general, the cluster DMFT results were checked with this when you increase the number of sites. But I think it's not very easy to do that, but it's possible, yes. Yes, yes.
A couple of quick questions. First, in one of the slides, when you have not doped it, in the half-field case, you see some kind of non-Fermi liquid like self-energy with this. But what I'm confused is that even for the metallic phase, when you believe that it is more like a Fermi liquid, right, with omega square, why is there a constant at zero frequency? Why is not non-zero?
Not going to zero?
Yeah. If it's non-zero, it's non-Fermi liquid. You don't have to worry about omega dependence. You have a dissipation for a fermionic system. That is very exotic.
Is this numerical problem, or is this with d prime equal to 0.1? Sorry? The thing here? We have to do this analytic continuation.
Oh, okay. So just something you add by hand to stabilize the analytic continuation.
Yes.
I see. Okay. So in principle, now that if you subtract this eta out of your result,
yeah,
both of them actually go
we
to
have
zero.
This, right?
Right. Both of them go to zero, right? If you go back to the previous slide.
Because they are related, right?
Right.
The self-energy and the spectral function.
I see. So I should renormalize my zero to the bottom or to the top of the red band. Okay. All right. The second question is that you have this result that at large T prime, you get this pseudo-gap phase, right?
Yes.
Right.
Yeah.
This is something that, since this half field, you should be able to check this with a Monte Carlo simulation. There is no sign problem here, right?
No.
Or there is?
Well, we are not using Monte Carlo.
This is with T prime?
With 2 prime,
oh, okay,
yes.
okay.
T prime or minus
-0.1
0.1 here.
All right. So you probably cannot. I'm just wondering whether there is another way to verify this result. Because this is a DMFT approximation, right? So
yes.
You need to collaborate with another method to make sure that this is real.
Okay.
Carol, I was just a bit confused when you have shown the experimental results for the value of P star for the compounds. They were not, yes. So this is not around 11%, right? In your plot, your P comes at 0.11. The transition from electron hole, yes, there. It's 0.11, 0.12, right?
Okay. No, but here is the coincidence, right? Because this is 45 degrees. So if you look, this quantity, it's 0.2 here, and it's 0.2 here. Okay? That's why what we are saying that we are in agreement with the experiments, because this quantity coincides with this one. Okay? And this happens for all these values of dopings, different values of doping. See, this one is a bit farther. It's the situation where P star is smaller than PFS, in agreement with this other value of T prime, right? So this was not on the top, over that straight line where the two quantities are equal.
So
So the point is that these two quantities are equal, even if I change PFS here.
Okay, but the value that you get there for P star is not the value where you should get it at t equals 0?
But, well, this is for a real material, right? We are not really taking,
yes,
it's
but
a
exactly,
model.
because I remember some previous data from ZX where he found that the transition between electron-like and hole-like was precisely at 1/8, which would be 12%.
No, but we are talking about charge density waves here. 1/8. Is another transition.
Well, he was looking at Hall data. When you look at the sign of your charge carriers, this is long ago. It's more than 10 years ago. And he was saying that the changing sign would be at around 12%. Well, this is something else, right? The 1/8 charge density wave is not only at 1/8, it's also at 10%, 12%, 15%. I mean, these you have neutron scattering data for LASCO, for Tranquada. And it's not LASCO what he had. I think he had BISCO. I don't remember which was, but I remember that he did these measurements. And he had something that was around 0.11. So that's why I was just a bit puzzled by those
Well, here
values.
there are different compounds, right? And then it happens at different points.
But they are much larger, right? That's kind of strange for me. That's why I was confused. No, he was not talking. Of course he knew.
Maybe
Well, there was Kaptulnik
try to
experiments
find
at
the
that
paper.
time. People denied it, but there were Kaptulnik experiments. Of course, not everybody was believing, but they were there. Yes, yeah, sure. Yeah, some people were just slow, but it's still. Yes, but his experiments was about the charge of the carriers, and it's precisely what you get. One should maybe just check it.
Okay, thank
and
you.
I would like them to understand those ones.
Okay, thank you.
Sorry.
Any other questions? So let's thank Carol again. We have a coffee break now, and we'll be back in 20 minutes.